Okay, before I get on to planes, I want to clarify a couple of things about lines. We have these three forms to write the equations of a line: the vector form, parametric form, and symmetric. And to write them, all I need is a point on the line or position vector to it and a direction vector A. So point and a direction vector, I can write any of these three equations of a line. It also goes the other way. I mean, if you look at any of these three forms, you know a point on that line and that direction vector of the line, or a vector parallel to the line. Like take the parametric form. The point are these little numbers here: x1, y1, z1. That's the point along that line. And the direction vector is these things in front of the t's. A1, A2, A3 is the vector parallel to the line. In the symmetric form, things subtracted off are the points. So minus x1, that means the point is x1, y1, z1. And the direction vector is this denominator, A1, A2, A3. If any of them equals 0, well, we have that exception. Just see, like, for example, y equals y1 instead of it being here. That means the A2 term is 0. And for the vector form itself, the point is this guy, and the direction vector is that. Okay, now on to planes. Okay, here's a plane out there in a coordinate system. We have x, y, and z. A point up there, we could describe it with position vectors. So P1 has position vector R1 to it. The generic P in the plane, pointing the plane P, is a position vector R. So this little difference vector, R minus R1, is a little vector in the plane. Now this normal vector, what does normal mean? The normal vector to a plane is perpendicular to every line in the plane. That's what it means to be normal. You can visualize that. A plane is flat. Normal just means perpendicular to anything. So that it's perpendicular to any line in the plane, and it's perpendicular to this particular line in the plane, vector in the plane. So we have this relationship, and dotted, because they're perpendicular, their dot product is 0. So this describes the plane. And if I break out what these mean in component parts, say n is vector ABC, and then R minus R1 would be those three components: x minus x1, y minus y1, etc. So here then is the equation of a plane. If I use this form to generate it, I would get this form, another form of the equation of a plane. I could also lump all the constant stuff up in this E here, and I could write it this way too if I wanted. So any of these three is a way to write the equation of a plane, and what I needed was a point in the plane and its normal vector. So how do I get that normal vector? Well, I can be given two vectors in the plane, and they can't be parallel. We'll talk about that in a minute. Are 3 points in the plane that are not collinear. If they were collinear, you couldn't write the equation of a plane. You don't really have enough information. Well, let's say I have 3 points in the plane. So I can write these little vectors, R3 minus R1 and R2 minus R1, to describe this little vector here and this little vector here. Those are two vectors in the plane. So if I cross them, they're in the plane, so the cross product will be perpendicular to the plane. So the way to find this n is to cross each of the R sub 2 minus R1 cross R sub 3 minus R1. So I just pick one of the what are the 3 points given and subtract them off from the other two and then cross them. So if given 3 points, here's how you do it. Find an equation of a plane that contains these 3 points. First, express all these points as position vectors, which means we change the parentheses to these angled brackets, notation-wise. But I need to form these different vectors. So I'll pick one of the 3, and I'll pick this third guy here, -1, -1, 4 is the reference. So I'll define my A vector as 3, 5, 2 vector minus this point. And I get 4, 6 minus 2. And the B vector is this point minus this vector. I get 3, 4 minus 3. So I have my A and my B vector. So I cross them. Step 2 is crossing them. Crossing this vector with this vector, A cross B. Do that arithmetic. I get this cross product. And that is my N. Or this is, or any scalar multiple of this guy is a valid N. So step 3 is to write the equation of the plane, and I'll use this format right here. So the things outside the parentheses are the components of the normal vector. -10, 6, -2. And inside the thing will be x minus something, y minus something, and z minus something. I need to pick one of the 3 points. I'll pick 2, 3, 1. I could have picked any of the 3. So there is the equation of the plane. You could do other arithmetic, and these are two other valid answers that don't quite look like this. This is usually the way I wrote. Planes are parallel if their normal vectors are parallel. So let's say you're asked, write the equation of a plane that's parallel to the plane we just did, but contains the point 1, 2, 3. So we go back to the same general format of a plane. Normal vector is what goes outside the parentheses, and we had, remember this, or any scalar multiple. I can divide by, let's see, -2 and get a 5, -3, 1, right? Well, I have 5, -3, 1. And then the point was 1, 2, 3. So x minus 1, y minus 2, z minus 3. Simplified like this, but this is an adequate answer in my class. What if the 2 vectors in the plane they give you are parallel? Well, let's say they say, okay, these 2 lines are in the plane. This is a line, equation of a line in symmetric form. This is the equation of the second line in symmetric form. Remember, you can pick up those direction vectors by looking at the denominator, 6, 4, 8, 3, 2, 4. Well, 6, 4, 8 is just twice 3, 2, 4. So right there, I know they're parallel. If I went through and calculated the cross product, I would have got a 0, and I'd have been stumped if I just tried to blindly follow the process we just talked about. So what do I do if I'm asked for this? First, find the equation of a plane that contains those 2 lines. Well, I can't just cross those 2 vectors, but what I can do is I can find another vector that's not parallel to those guys by taking the difference between 2 points along those lines. And get the points from the numerators. I'm going to have a -4, 6, 10 is 1 point, and a 1, -1, 0 is another point. So if I take the difference between those 2 points, I get this vector. This vector now is not parallel to the other vectors. So I can cross this guy with either 6, 4, 8 or 3, 2, 4. Doesn't make any difference. I'll cross 3, 2, 4 and this guy. And -8, -50, 31, and that's my normal vector. So now I can write the equation of the plane. Outside the parentheses will be -8, -50, 31. Inside the parentheses, I'll pick a point. 1, minus 1, 0. So x minus 1, y plus 1, and just plane. That's the equation of the plane. For the line through a point and perpendicular to this plane, perpendicular to the plane would be the normal vector. So that's my direction vector. It's the normal vector. In parametric form. So the normal vector will be the things in front of the t. So -8, -50, 31t. Or the x, y, and z equations. The things out front will be one of the 3 points, one of the 2 points. One from this, -1 from that. So I'm picking either 1, -1, 0, or -4. I picked. Anyway, that I think finishes it off. Lines and planes and the entire vector review, which is module 3 of EnMath A.